Trapping parameters in KMgSO4F x equals Cu, dy, and EU. Abstract KMgSO4F, Cu, KMgSO4F, dy and KMgSO4F, EU material are synthesized by wet chemical method and studied for its trapping parameters such as geometrical factor, order of kinetics, B, trap depth, E, and frequency factor, S, associated with the isolated TL glow curve by Chens half-width method to get the information mechanism of trapping and recombination of charge carrier with the traps. Thermoluminescence, TL, glow curve of KMgSO4F, Cu/dy/EU has been investigated in detail at various concentrations, between the temperatures range of 50 to 300 OC. All TL glow curves showed single peak at 197.76 OC, 172.91 OC, and 180.26 OC respectively. The release of hole or electron from defect centers at the characteristic trap site indicates the luminescence process in this material. 1. Introduction. Most research of TL concentrates on the development of new phosphors exhibiting improved performance and on measuring set UPS1. CaF2 doped with rare earth impurity ions was extensively studied because of its high sensitivity and its ability to store the incident energy 2 to 3, which is suitable for radiation dosimetry. The material has been marketed as a commercial thermoluminescence, TL, dosimeter, CaF2dy, under the commercial name TLD200. TL technique has a wide range of applications such as radiation detectors, solid-state dosimeters for industrial and medical radiation dosimetry applications, dating techniques in archaeology, geology, and to study the variety of defect centers created by ionizing radiation 4 to 9. Till date no material has been found to possess all features, and thus a search in this area is in constant progress. The present work is also a small step taken forward in the same direction for a search of an ideal TL phosphor. Sulfate-based TL materials are synthesized and studied because of their well-desired characteristics like a high temperature low peak, linear response with ionizing radiation exposure, negligible fading and an easy methods of preparation. 10. There are several thermoluminescent materials such as CaSO4, EUAG, K2Ca2, SO4, 3EU, KMgSO4Cl doped with dy, Ce, and Mn etc., of which almost all has been studied for improvement in the thermoluminescence characteristics and the trapping parameters. 11-13. Many researchers have investigated luminescence properties of mixed sulfate phosphors for their use as dosimeters of ionizing radiations. 14-20. In three-parameter model, TL is described by the three parameters, namely activation energy, E, order of kinetics, B, and frequency factor, S. This work reports for the first time the TL response of the phosphors to gamma radiation in mixed halosulfate phosphor KMgSO4F doped with different concentration of the copper, dysprosium, and europium prepared by wet chemical method. The focus in this paper is mainly on studying the trapping parameters such as geometrical factor, hence order of kinetics, B, trap depth, E, and frequency factor, S, all have been calculated by Chens method for 5 GY dose of 60 CO for heating rate of 50/C. According to a theoretical analysis of thermoluminescence, TL, phenomenon done by Randall and Wilkins. 21, electrons are trapped during thermal excitation at some lattice sites. When the crystal is heated, electrons are released into the conduction band and recombine with holes at the recombination sites, resulting in TL emission. In practice, phosphors have more than a single trap and a single recombination center, which results in a curve of TL. TL investigations have also shown that defect centers play a crucial role in TL analysis. The formation and the stability of the defect centers depend on the method of preparation of phosphors and the activators. TL strongly depends on the host material, the type of activator, radiation-induced defect center, dose, and type of ionizing radiation. Dosimetric characteristics of TL materials are mainly depends on kinetic parameters. Kinetic parameters quantitatively describe the trapping emitting centers responsible for the TL emission. Therefore, determination of the kinetic parameters is an active area of research for better understanding of TL process. There are various methods for evaluating the trapping parameters such as glow peak shape, various heating rates and initial rise method. 2. Experimental. KMgSO4F, pure, and KMgSO4F Cu phosphors were prepared by a wet chemical method. MgSO4 and Kf of AR grade were taken in a stoichiometric ratio and dissolved separately in double distilled deionized water, resulting in a solution of KMgSO4F. Confirming that no undissolved constituents were left behind and all the salts had completely dissolved in water and thus reacted. MgSO4 and Kf. KMgSO4F. Then water-soluble sulfate salt of copper was added to the solution to obtain KMgSO4F Cu. The compounds KMgSO4F, pure, and KMgSO4F, Cu in its powder form was obtained by evaporating on 80 OC for 8 hours. The powder was used in further study. The same procedure was adopted for KMgSO4F, dy and KMgSO4F, EU. In this case instead of copper the sulfate salt of dysprosium or europium was used. Formation of the compounds was confirmed by taking the X-ray diffraction, XRD, 22. X-ray diffraction pattern, XRD, of KMgSO4F. Prepared material did not indicate presence of the constituents MgSO4 or Kf and other likely phases. These results indicate that the final product was formed in homogeneous form. Taking the same amount of samples, 5 mg, thermoluminescence, TL, emission spectra were recorded using nucleonics thermoluminescence reader, integrated PC-based, TL 10091. 3 results and discussion. 3.1 Analysis of trapping parameters. Fig 1 discusses multi-level TL model for competing trapping and luminescence centers. The shallow traps get emptied earlier and the deep traps, acting as a reservoir, may replace them subsequently, or they also can go directly to the conduction band and recombine with the luminescence centers during their back journey. 23. Here on the basis of the TL results the trapping parameters were calculated by Chens half-width method. Fig 2 shows a glow curve for the sample KMgSO4F Cu quenched at 250 OC then exposed to radiation from 60 CO source at room temperature for 5 GY at the heating rate of 5 OC/S and a dose rate of 0.36 kGY/HR. TL glow curve of KMgSO4F dy and KMgSO4F EU are shown in Figure 3 and 4. Single prominent TL glow peak has been observed at about 172.91 OC and 180.26 OC respectively, when exposed to rays for 5 GY at the rate of 0.36 kGY/H1. The TL glow curves of all irradiated KMgSO4F, X equals Cu or dy or EU, samples show single glow peak indicating one set of trap is being activated within the particular temperature range due to irradiated effect. In this study Chen's peak shape method has been used to analyze the glow curves of KMgSO4F Cu, KMgSO4F dy and KMgSO4F EU halo phosphors. For kinetic and trap depth analysis TL glow curves were recorded at a heating rate of 5 Ks1. All the samples were exposed to a low dose of 5 GY. The measured glow curves were analyzed to resolve the individual peaks, assuming first order, second order, and general order kinetics. The order of kinetics and activation energy of the isolated peak was found using Chen's set of empirical formulae. To determine the order of kinetics, B, and the symmetry factor, given by Chen was made 24 to 25. 3.1.1 Order of kinetics, B. Order of kinetics was determined by calculating symmetry factor of the glow peak by measuring the values of T1 T2 and trademark equals D slash equals T2, trademark slash T2 T1. 1. Table 2 gives the values of T1, T2, and trademark of glow curve of KMgSO4F Cu, KMgSO4F dy and KMgSO4F EU halo phosphors. Putting these values in EQ.1 symmetry factor is calculated and shown in Table 2, it suggests that all the peaks obey second-order kinetics. The calculated values of kinetic parameters are listed in Table 2. Moreover, Ballerine and Ferretta have proposed the following factor 26 equals D slash T equals T2, trademark slash trademark T1. 2. This parameter ranges from 0.7 to 0.9 for the first-order kinetics, and from 1.05 to 1.20 for second-order kinetics, Ballerine parameter. And the geometrical factor, calculated by Chen's method shown in Table 2. The geometrical factor is 0.52 and Ballerine parameter, is laying in between 1.05 to 1.20, indicating that it obeys second-order kinetics. This means, in principle, that a retrapping effect should be present. 3.1.2 Activation energy, E. Activation energy was calculated by using Chen's equations, which gives the trap depth in terms of T, D. A general formula for E is given by E equals C, KT2M slash, B, 2 KTM, 3. Where is T, D, or are the constants C and B for the three equations, T, D, or. They are calculated total half intensity width equals T2 T1, the high temp half width, D equals T2 trademark, and low temp half width, T equals trademark T1, where trademark is peak temperature corresponding to maximum intensity, T1 and T2 are temperature on either side of trademark corresponding to half of maximum intensity. The trap depth was calculated by the Chens equation, where E is trap depth and C and B are constants of Chens equation, was replaced by T, D, or, as per the case. Chens method does not require knowledge of the kinetic order, which is found by using the symmetry factor from the peak shape. The values of C and B are summarized as below. CT equals 1.510 plus 3.0, 0.42, BT equals 1.58 plus 4.2, 0.42. CD equals 0.976 plus 7.3, 0.42, BD equals 0. C equals 2.52 plus 10.2, 0.42, B equals 1. With equals 0.42 for the case of first order TL glow peaks, and equals 0.52 for the case of second order peaks. For second order kinetics, the values of T, D, and are tabulated in Table 1. The activation energy E, F, has been calculated with the equations for second order kinetics. The values of E are given in Table 3. Growiner analyzed the TL curve for the second order kinetics and derived the formula for the trap depth, E, as E equals GKTM T1/T 4, where G equals 1.51, T equals trademark T1, where trademark is the temperature of the TL peak maximum intensity, IM, and T1 trademark is the temperature at the TL intensity I equals 0.5 IM. It has been observed that the values of trademark has been shifted to higher temperature side after doping the compound. 3.1.3 Frequency factor, S. Frequency factor was calculated by the equation given by Chen and Weiner. SSE/KT2M equals S1 plus, B1, 2 KTM/EEXP, E/KTM, 5. Where SS is heating rate, K is Boltzmann's constant, taken as 8.617 x 10-5. The frequency factor was calculated by the equation, 5. Conclusion. Wet chemical synthesis is easy process to prepare phosphors KMgSO4F KMgSO4F and KMgSO4F as a TL material. The TL glow curve of irradiated KMgSO4F compound has the simple structure with the prominent single TL glow peak at 197.76 OC, whereas KMgSO4F and KMgSO4F have at 172.91 OC and 180.26 OC respectively. Single glow peak in this compound indicates only one set of traps is being activated within the particular temperature range. The glow curves of KMgSO4F KMgSO4F and KMgSO4F obey the second order kinetics. The activation energy E and frequency factor S have been calculated with the equations for second order kinetics. The kinetic parameters calculated by Chen's half-width method. These studies indicate that the KMgSO4F, SAD phase, Cu, Dy, and Eu, phosphor have potential for its use in radiation dosimetric applications.